brilliant. Okay, so non-perpendicular vectors, we're now going to have to add x and y of each, and it's really a bookkeeping thing. We're going to start off with a simpler version of a sample problem, and then we'll go to sample problem 3C in the book on page 95. Okay, so you take a train 40 kilometers at 37 degrees north of west, then the tracks turn and you go 25 kilometers at 37 west of north, then 25 kilometers at 15 north of west. What's your resultant displacement? What's your overall displacement? So the first thing we have to do, always, 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 is draw the picture. No. Okay, so we're going to start off. Every time we start off one of these problems, what I do for myself is I draw myself a little compass rose as a start point. Okay. Good luck with that. And I draw myself my little angle. And my line. Actually, I could make that line longer. And these don't have to be, yeah, this is west of north. This is 37 west. Oh, good heavens, it is. Okay, so we've got 37 west of north for 40 kilometers. And then it turns. And so what I tend to do is I draw myself another little compass rose, and I'm going to draw it in a contrasting color just to help us out. And now we go 25 kilometers at 15 north of west. So now I'm doing, well, that's a pretty low angle. And this is not a tremendously large angle. And you don't have to draw these perfectly to scale. It helps to draw it as much to scale as possible, only because you can trick yourself visually if you don't. So, you know, try to be at least somewhat to scale, but you don't have to fuss over it with a protractor or anything. Okay, and this we do for 25.0 km. So we have two vectors. They are not perpendicular to one another, and our resultant is going to be something like this. So how do we get that resultant? We have to we basically have to resolve each of the vectors into their x and y components and then add up the x and y components. I tend to color code these things. My apologies right off the bat to anybody for whom that's not real effective, but oops. So I'm going to start with my first triangle. This is why these get kind of hairy. So I'm breaking apart that first vector into its x and y components. And I'm going to label these. This is displacement on the x, number 1. This is displacement on the y, number 1. We're going to have multiple x and multiple y displacements. So good labeling, good color coding, good bookkeeping is really essential. And I'm going to actually move my picture. So the other thing I do is I tend to try to color code my calculations. Like I'll make a highlighted box around my calculations that pertain to one vector. So here we're dealing with that first vector, and we're breaking it apart into the x and y displacements. So we can go ahead and handle the dy1 first. Well, what do we have? We have the hypotenuse and we have the angle. What trig function can we use to get the adjacent side? Cosine, anyone? Right. Because we know that the cosine of theta is equal to the adjacent over the hypotenuse. And in this, that's going to equal the displacement y on the displacement on the y1 over our 40.0 kilometers. So we can solve that and say that cosine of theta times 40.0 km equals dy1. We get 31.9454204 kilometers equals dy1. You're going to want to keep all those numbers for now because, of course, you won't take sig figs till the very, very end. If you're using one of the TI multi-views, it's easy enough to write down the first 4 and then ... so that you can go back and look it up on the calculator. Okay, well, that's our first step. Well, now we need to figure out our displacement x for the first vector. So we have an opposite side, a hypotenuse, and an angle. What trig function are we going to use? Sine. So we know that the sine of theta is equal to the opposite over the hypotenuse, which in this case is going to equal our dx1 over our 40 kilometers. So the sine of 37 degrees times our 40 km will be equal to our dx1. Okay, calculate. Okay, so we get 24.07260093 kilometers is equal to our dx1. Okay, other things I'm going to tend to do, here let me move that. I tend to circle my intermediate answers for myself because you're going to have to go back and find those numbers. The other good reason to circle your intermediate answers is so that I can find them, so that when I'm grading and giving you partial credit, I can easily locate, oh, okay, well they had this displacement right, they had that displacement right, okay, their error came in the next step. It makes my job easier. You don't have to do it, but boy, I sure do appreciate it. Okay, again, things you can't do on paper. I'm going to move this whole thing. Yeah. You get partial credit, yeah. Yeah. Okay, I'm just trying to move this whole thing. No. Hold on. Okay, so now I need to find the displacement on the x2 and the displacement on the y2. So I'm now looking at, oops, that and that. These are terribly drawn. So I've got dx2 dy2. So we have our first serious challenge here. Oh, you know what? That's because I misdrew it. So tell me what my problem is with the way I drew it. Yeah, I put them on the wrong side. That's a really common mistake. I just made it. Can you do it that way? Yeah, it just takes extra brain power to sort everything out and flip everything around. So you can certainly do it that way. We're gonna redraw. Yeah. Were you drawing in pen? Yep. Ooh. What I very often do is I draw in pencil and then I highlight once I know it's right. You might want to pick some up. They're really cheap at Dollar General. So here, because the 15 degrees is below that line. So you could use the complement and do that. It just takes extra brain power, and it's a really easy way to screw things up. So we're now going to use, yeah, the first triangle is right. The second one is the one I screwed up. So we're going to do that, and then that 15 is inside our triangle. You can use the other angle. It's fine, but I would advise initially just sticking with the angles you're given, just because it takes extra. It's one more level of bookkeeping that you have to engage in, and that's kind of rough. So that's dx2. This is dy2. Okay, so we have our 15-degree angle. We have our hypotenuse of 25, and now we want to find out what our x displacement is. So we've got an adjacent, and we've got an angle and a hypotenuse. What would be our trig function? Pardon? We're doing dx2. So the adjacent, so we would use cosine. We know cosine of theta equals adjacent over hypotenuse. And in this case, that will be dx2 over 25.0 kilometers. So we can solve that for dx2. Cosine of 15 times our 25 kilometers equals displacement on the x2. Okay, so I'm getting 24.14814566 kilometers is our second x displacement. I'm going to circle my intermediate answer. And then I'm going to move that down to make room. Okay, so we got our dx2. Now we need our dy2. So we know we're going to use sine because dy2 is the opposite of the angle. Oops. So we have sine of 15 degrees will be equal to dy2 over 25.0 kilometers. Sine of 15 times 25.0 kilometers will equal dy2. Okay, so I'm getting 6.47047612 kilometers is dy2. Now, we've got all those figured out. What next? I'm glad you asked. Now we have to actually figure out our overall x and y displacement. So I'm going to go ahead and get rid of the text of the problem. I think we've got it committed at this point. I know, but it's okay. So I'm gonna pick up a third color here for my resultant, and very traditionally, very often red is used for resultants. You don't have to, it doesn't matter. So we know that the x displacement total is equal to dx1 plus dx2. Agreed? Okay. Now, in this problem, and the reason that I made one up rather than use the one in the book, the x displacements are all heading in the same direction, and the y displacements are all heading in the same direction. So it's a simple matter of addition. Okay? One of the things that I very often do for myself when I'm solving these is I put a little arrow next to my answer that indicates visually to me which direction this travel is. So for my dy1, it's up. For my dx2, or I'm sorry, for my dy1, it's north. For my dx1, it's west. For my dy2, it's north, and for my dx2, it's west. So they're all heading in the same direction, okay? Which makes it very simple. You don't have to worry about sign or anything else. Obviously, I'm telling you this because this will not always be the case. You probably guessed that. So let's go ahead and do the math. Okay, so just pulling those numbers down off my calculator and adding them up is the easiest way to do it. So I get 48.22074659 kilometers is the total displacement on the x-axis, and that is to the west. Okay, or I'll draw myself a little arrow. Okay, 5 steps down, 3 to go. So our dy total, of course, is going to equal our dy1 plus our dy2. And again, just using the calculator to pull them down. Okay, so pulling the numbers off the calculator, I get a dy total of 38.41589.653 kilometers north. Now, 6 calculations later, we're ready to actually approach solving our final answer, which is our resultant. I know, it doesn't actually. And what I'm going to do is I'm going to copy the image and those calculations to a clean slide so that we have a little bit more space. Well, no, you know what, I'll just shrink the calculations on the bottom. So now what I very often do for myself is I redraw what I'm viewing as my larger triangle. And so this is my dy total. Okay, so now we're ready to find our resultant. So now we're actually just down to a simple right triangle. So this is easy Pythagorean theorem because our resultant is equal to the square root of dx total squared plus dy, total squared. Okay, so we've got it all plugged in. Again, using the multi-view makes it really easy to just pull numbers down. Okay, so we've got the magnitude of our resultant, 61.652425 kilometers. Now we just need a heading. We need an angle. Okay, so now we just need to get our heading, and you remember how I said don't rely on numbers that you computed to get your heading? Well, you computed all of these. You know, you can't really go back to the originals, but you're better off to take those. So we know that the inverse tangent of opposite over adjacent, TOA, so dxt over dyt will give us theta. Okay, so we get 51.4568159 degrees is theta. How does our final answer look? Well, it's 2 sig figs. So it is 62 kilometers at 51 degrees what? 51 degrees west of north, because we're looking at this angle. So that's our final answer. It's a whole bunch of steps. It's a whole bunch of steps. It's a whole lot of chances to screw it up. So you really do have to be careful. And again, the bookkeeping is critical. So now let's do one that throws in an added complication. We're going to go to 5C, page 95 in your book. Okay, so the problem, a hiker walks 25.5 kilometers from her base camp at 35 degrees south of east. On the second day, she walks 41.0 kilometers, 65 degrees north of east, at which point she discovers the Ranger's Tower. What's the magnitude and direction of the resultant displacement between base camp and the Ranger Tower? So the first thing to do always is to draw your picture. Whoops. And, you know, I'm going to start off with my little cheater compass rose. And we know that she is going south of east. So something like that. And that angle is 35 degrees, and we're only given 2 sig figs. And the displacement on that first leg is 25.5 kilometers. And then I'm going to draw another little compass rose to help me out, because the next day she goes at, this is a 65 degree angle, 65 north of east, and she goes 41 kilometers. And I gotta say, that's quite a hike. 41 kilometers is a big day. Okay, so there's our picture, and what we're looking for is that resultant displacement. So this will be the displacement resultant. And sometimes it's actually helpful to visualize. I occasionally do this where I will try to visualize the resultant triangle first. So if I kind of visualize what the overall x and y are going to be, it tells me, for one, and I already knew this, that there's going to be some subtraction involved, because on the y-axis, my whole first vector, the y displacement is to the south, and on my second vector, my second leg, my y displacement is to the north. So there's going to be some heavy-duty bookkeeping here. Okay, so I'm going to deal with this first displacement first. And if I draw my triangle like this, then that 35-degree angle is inside the triangle. You know, that said, you're certainly welcome to use the other angle, but it's more mental gymnastics. So I know that it's a way that I can usually manage to screw myself up pretty well. So on the initial leg, we want to find our dy and our dx, and dy is going to be using which trig function? It's opposite the angle. So sine. So we know that the sine of theta will equal our dx1. Yeah, absolutely. Over 25.5 kilometers. And as has been duly pointed out, I screwed that up. Sine is going to be our y displacement. dy1. Sine theta equals dy1 over 25 kilometers. So sine theta times 25.5 kilometers will give us our dy1. Okay, so I've got my result, my displacement for my dy1, and I drew that little arrow in next to it for myself, and I'm going to circle it so that I can keep track of it. And remember, this is to the south, so you can stick your S in there, you can put your arrow in there. Do something for yourself to help you keep that straight. So now we'll go ahead and find our dx1. Cosine of theta equals dx1 over 25.5 kilometers. Cosine theta times 25.5 km equals dx1. So we've got 20.8883771 kilometers east is our dx1, and I drew my little arrow in there to help keep track of which way that's going. So now we want to deal with the second leg of our trip. And I've drawn little triangles in there with sort of a dotted line. So I've drawn the triangle so that that angle is inside the triangle, so that we can just use that angle without having to do any complicated anything else. It's complicated enough. So this is my dx2, and this is my dy2. Okay, and to find dy2, here we're going to use sine, because the y displacement is opposite the angle. So sine of theta is equal to dy2 over our 41 kilometers. So sine of theta times 41 kilometers will give us our dy2. Okay, yeah, and that's to the north. So we'll go ahead and circle that answer like that. So now we're ready to find our dx2. Okay, so we're going to use cosine because the x displacement is adjacent to the angle. So cosine of 65 degrees times 41.0 km will give us our dx2. So we've got 17.32734, etc. kilometers east is our dx2. So now we're ready to do our big overall. And it's helpful, of course, to label these. So this red line here is our dx total, and this red line here is our dy total. Okay. Let's shrink. Okay, so dx total is going to equal dx1 plus dx2. dx1 and dx2 are going in the same direction. And what I very often do for myself to help keep myself out of trouble is when I write that overall equation, I will put a little arrow under or next to my individual displacements, because that helps me not screw up. Okay, so we add up our two displacements on the x. We get 38.2157, etc. kilometers to the east. So again, with my stupid little arrows. Now let's do our dy total. This one is a little bit more challenging because, of course, dy1 is south. It's, you know, what looks like down on our page. And dy2 is north. So what that tells you is that one of them needs to be a negative. One of them is going to have to be subtracted from the other. Conventionally, of course, we use anything that's the up on the y-axis as a positive. And here that works out nicely because that's our larger number, which gives us a nice positive answer, and we like that. It makes our brain feel happy. We'll talk about cases where that's not true later. We don't need to right now. So dyt is equal to, okay, so you're going to subtract dy1 in essence, or make that a negative, you know, negative 14.62, etc., plus 37.1586. However you want to actually do the calculation is fine, but you know that dy1 has to be a negative because it's in opposition to the other one. Is everyone good with that? Okay, almost to the last. Okay, so we've got this set up. It's Pythagoras at this point. The resultant displacement is going to equal the square root of the total x displacement squared plus the total y displacement squared. So we get a magnitude of 44.3638, etc., kilometers. One thing left. Heading, getting a direction. So we'll use the tangent function again. And we know that the inverse tangent of our dy, opposite or adjacent, dy total over dx total will give us theta. Okay, so magnitude of the angle, 30.5204. What's the heading? What's the heading? North of east. Yeah, north of east. So our final answer, and we only have, what, 2 sig figs, would be 44 kilometers at 31 degrees north of east. Okay?
Took 40 minutes.
Yeah. Okay, so I'll give you some time to work on your own on the 3C packet. Remember, I am tutoring tomorrow night. You're only having to do the odds on 3C, so I consider that a gift. Tomorrow, oh, and also in the book. So in the book, 2, 3, and 4 on page 97. 2, 3, 4 on page 97. Yeah, the ones in the book are not terrible. So, and then you'll have the rest of the day today. You'll have some time tomorrow to work on these. And then Wednesday we'll do a FIP quiz over these.